Look up at the night sky on a clear evening, and you'll see thousands of distant suns scattered across the darkness. Each one appears as a simple point of light, but behind that faint glow lies an entire world of nuclear fusion, magnetic storms, and cosmic violence. For most of human history, the stars remained utterly unreachable, distant beacons whose true nature we could only guess at. We knew they were far away, but we had no idea just how far or what separated us from our nearest stellar neighbours. The story of measuring stellar distances is one of astronomy's greatest achievements. It required patience, precision, and instruments sensitive enough to detect shifts smaller than the width of a human hair viewed from kilometres away. When astronomers finally succeeded in measuring the distance to the nearest stars in the 19th century, they discovered something humbling. Even our closest neighbours are separated from us by distances so vast that light itself takes years to cross the void between us. The nearest star system, Alpha Centauri, lies more than 4 light-years away, a gulf of 40 trillion kilometres that no human technology has yet crossed. But distance is only part of the story. Our stellar neighbourhood contains a remarkable variety of stars, from tiny red dwarfs, barely massive enough to sustain fusion, to brilliant white stars burning through their fuel at prodigious rates. Some are solitary wanderers like our Sun, while others orbit in pairs or even triplets, locked in gravitational dances that will last billions of years. A few are surrounded by planets, raising the tantalizing possibility that life might exist just beyond our cosmic doorstep. Others are the fading remnants of once mighty suns, cooling slowly into darkness as the universe ages around them. The quest to understand our nearest stars has driven the development of increasingly sophisticated instruments. Ground-based telescopes mapped their positions and spectra. Space observatories like Hipparcos and Gaia measured their distances with unprecedented precision. Infrared telescopes revealed faint brown dwarfs lurking in the darkness. Objects too small to be stars, but too large to be planets. Radio telescopes detected the flares and magnetic activity of red dwarfs, while spectroscopy unveiled the chemical compositions written in starlight. Each discovery has refined our understanding of stellar physics and galactic structure. By studying nearby stars, astronomers can test theories of stellar evolution, measure the density of matter in the solar neighbourhood, and search for patterns in the distribution of different star types. These stars also serve as laboratories for understanding processes that occur throughout the galaxy, from the birth of planetary systems to the death throes of aging suns. This is the story of our closest stellar neighbours, the techniques used to find and measure them, and what their existence tells us about our place in the cosmos. From the triple star system of Alpha Centauri to the faint red dwarfs that dominate our neighbourhood, from the white dwarf remnants of ancient stars to the brown dwarf failures that never quite made it, we'll explore the stars that share our corner of the Milky Way. These are not distant abstractions, but nearby objects we can study in detail, each one a window into the physics that governs every star in the universe. The challenge of measuring stellar distance. For thousands of years, humans looked at the stars and wondered how far away they truly were. Ancient astronomers placed them on a celestial sphere just beyond the planets, perhaps a few thousand kilometres overhead. Even the great minds of the Renaissance struggled with the question. When Copernicus proposed that Earth orbited the Sun rather than sitting at the centre of the cosmos, critics asked why we couldn't observe stellar parallax, the apparent shift in a star's position as Earth moved through its orbit. If Earth truly travelled millions of kilometres around the Sun, nearby stars should appear to move against the background of more distant stars, just as nearby trees seem to shift against distant mountains when you walk past them. The fact that no such motion could be detected suggested either that Earth stood still or that the stars were incomprehensibly distant. The truth was the latter, but proving it required instruments far more sensitive than anything available to early astronomers. The parallax angles of even the nearest stars are measured in fractions of an arc-second, less than 1/3600th of a degree. Detecting such tiny shifts demanded stable telescopes, precise measurements, and years of patient observation. Only in the 19th century did technology finally catch up to the challenge. The breakthrough came in 1838, when German astronomer Friedrich Wilhelm Bessel succeeded in measuring the parallax of 61 Cygni, a binary star system about 11 light-years from Earth. Using a heliometer, an instrument designed to measure small angular separations, Bessel tracked the star's position over several months as Earth orbited the Sunday. He detected a parallax angle of just 0.314 arc-seconds, a shift so small it would be equivalent to seeing a coin move by the width of a human hair from several kilometers away. From this measurement, Bessel calculated that 61 Cygni lay approximately 660,000 astronomical units, distant about 10 light-years, remarkably close to the modern value. Almost simultaneously, other astronomers achieved similar successes. Thomas Henderson measured the parallax of Alpha Centauri from the Cape of Good Hope in South Africa, determining it to be the closest star system visible to the naked eye. Friedrich Struve measured the parallax of Vega, one of the brightest stars in the northern sky. These three independent measurements, all published within months of each other, finally answered the ancient question of stellar distance and revealed the true scale of the cosmos. The stars were not thousands of kilometers away, but trillions distances so vast that light itself, traveling at 300,000 kilometers per second, required years to traverse them. The principle behind parallax measurements is elegantly simple. As Earth orbits the Sun, our viewing angle changes by up to 300 million kilometers, twice the distance from Earth to the Sunday. This creates a baseline for triangulation. By measuring a star's position in the sky 6 months apart, once on each side of Earth's orbit, astronomers can calculate the angle through which the star appears to shift. The smaller the angle, the more distant the star. 1 parsec, the standard unit of stellar distance, is defined as the distance at which a star would have a parallax of exactly 1 arc-second. It equals about 3.26 light-years, or roughly 31 trillion kilometers. However, parallax measurements become increasingly difficult with distance. Beyond a few hundred light-years, even the most precise ground-based telescopes struggle to detect the minuscule angular shifts. Earth's atmosphere distorts starlight, causing images to shimmer and blur, an effect called astronomical seeing. Even on the clearest nights at the best observing sites, atmospheric turbulence limits the angular resolution to about half an arc-second, making precise parallax measurements impossible for all but the nearest stars. The solution came from space. In 1989, the European Space Agency launched Hipparcos, the first space telescope dedicated to measuring stellar positions. Operating above Earth's atmosphere, Hipparcos could measure parallaxes with a precision of about 1 milliarc-second, 1,000th of an arc-second. Over 4 years, it measured the positions and distances of more than 100,000 stars, extending precise distance measurements out to several hundred light-years and creating the first 3-dimensional map of our stellar neighborhood. But even Hipparcos had limits. The real revolution came with Gaia, launched in 2013. Gaia's instruments are so sensitive they can measure parallaxes to within a few micro-arc-seconds, millionths of an arc-second. This precision is equivalent to measuring the width of a human hair from 1,000 kilometers away, or detecting the motion of a person walking on the moon as seen from Earth. Using this capability, Gaia has measured the positions and distances of more than 5 billion stars, creating an unprecedented census of the Milky Way's stellar population. Through Gaia's data, astronomers have refined the distances to our nearest stellar neighbours and discovered new ones. The measurements reveal not just where stars are, but how they move through space, their proper motions and radial velocities. By combining position, distance, and motion, astronomers can reconstruct the three-dimensional structure of the solar neighbourhood and trace the orbits of nearby stars backward and forward in time. Some stars currently far away once passed much closer to the Sun, while others now nearby will eventually drift into the distance. The stellar neighbourhood is not static, but constantly evolving, a dynamic system shaped by the gravitational currents of the galaxy. Alpha Centauri, our nearest stellar neighbour, at a distance of just 4.37 light-years, Alpha Centauri is the closest star system to our Sun. On clear nights in the southern hemisphere, it appears as one of the brightest stars in the sky, a brilliant yellow-white beacon near the constellation Centaurus. But Alpha Centauri is not a single star, it's a triple system. 3 stars bound together by gravity, orbiting one another in an intricate cosmic dance that will continue for billions of years. The 2 brightest components, Alpha Centauri A and Alpha Centauri B, form a close binary pair. Alpha Centauri A is slightly larger and more massive than our Sun, classified as a G-type main sequence star with a surface temperature of about 5,800 Kelvin. It's remarkably similar to our Sun in many respects. Its mass, luminosity, and spectral type all match closely, making it one of the most Sun-like stars known. Alpha Centauri B is somewhat smaller and cooler, a K-type orange dwarf with about 90% of the Sun's mass and a surface temperature of around 5,300 Kelvin. Despite their differences, the 2 stars orbit a common centre of mass once every 80 years, their separation varying between about 11 and 36 astronomical units, comparable to the distance between the Sun and Saturn. The third member of the system, Proxima Centauri, is far less conspicuous. This tiny red dwarf lies about 13,000 astronomical units from the Alpha Centauri AB, pair roughly 1,000 times the distance between Earth and the Sun, or about 1/5 of a light-year. At this distance, Proxima takes approximately 550,000 years to complete a single orbit around the binary pair, assuming it's gravitationally bound at all. Some astronomers have questioned whether Proxima is truly part of the Alpha Centauri system or merely passing nearby, but recent studies of its motion strongly support the idea that all 3 stars share a common origin and remain gravitationally linked. Proxima Centauri holds the distinction of being the single closest star to our Sun, just 4.24 light-years away, about 40 trillion kilometres. It's a small, cool star with only about 12% of the Sun's mass and a surface temperature of roughly 3,000 Kelvin. At such a low temperature, Proxima glows a dull red, emitting most of its light in the infrared spectrum. Despite being the closest star, it's far too faint to see with the naked eye. Its apparent magnitude of 11.1 requires a telescope to observe. Red dwarfs like Proxima are the most common type of star in the galaxy, making up about 75% of all stellar objects. They burn hydrogen so slowly that they can remain on the main sequence for trillions of years, far longer than the current age of the universe. Proxima Centauri has likely been shining for billions of years and will continue doing so for trillions more, long after our Sun has swelled into a red giant and shed its outer layers. In a distant future, when all more massive stars have exhausted their fuel and died, red dwarfs like Proxima will be the only stars left shining. The discovery of planets around Proxima Centauri has made it one of the most studied stars in astronomy. In 2016, astronomers announced the detection of Proxima Centauri b, a planet with at least 1.17 times Earth's mass orbiting the star every 11.2 days. The planet lies within Proxima's habitable zone, the region where temperatures might allow liquid water to exist on a planetary surface. This makes Proxima b the closest known exoplanet to Earth and a prime target in the search for life beyond our solar system. However, Proxima Centauri presents challenges for any potential life. Red dwarfs are magnetically active stars, prone to powerful flares that can erupt with little warning. These flares release intense bursts of ultraviolet and X-ray radiation, potentially stripping away a planet's atmosphere if it lacks a strong magnetic field. Proxima flares frequently, sometimes increasing its brightness by several times in just minutes. Any planet in its habitable zone would be subjected to these violent outbursts regularly, making the prospects for life uncertain. Additional planets have since been detected around Proxima. In 2020, astronomers reported the possible discovery of Proxima c, a more massive planet orbiting farther out, though subsequent observations have left its existence in question. In 2022, another candidate, Proxima d, was announced a small planet with only about a quarter of Earth's mass, orbiting even closer to the star than Proxima b. These discoveries suggest that planetary systems around red dwarfs may be common, and that even our nearest stellar neighbour harbours multiple worlds. Alpha Centauri A and B have also been scrutinised for planets, though with less success. In 2012, astronomers announced the discovery of a planet around Alpha Centauri b, but subsequent analysis revealed the signal was likely caused by instrumental artifacts rather than a real planet. Despite extensive searches using radial velocity and transit methods, no confirmed planets have been found around either Alpha Centauri A or B. This absence is puzzling, given that stars similar to the Sun often host planetary systems. It's possible that planets exist but have so far evaded detection, or that the gravitational interactions between the two stars disrupted planet formation early in the system's history. The Alpha Centauri system offers a tantalizing target for future interstellar exploration. At just over 4 light-years away, it's the closest star system we could conceivably visit with advanced propulsion technology. The Breakthrough Starshot initiative, announced in 2016, proposes sending tiny spacecraft equipped with light sails to Alpha Centauri. Powered by ground-based lasers, these probes could accelerate to 20% of the speed of light, reaching the system in about 20 years. While the technology remains decades away from realization, the concept demonstrates that even interstellar distances are not entirely insurmountable. Barnard's star, the fast-moving red dwarf. At a distance of just 5.96 light-years, Barnard's star is the second closest stellar system to the Sun and the closest solitary star. Located in the constellation Ophiuchus, it's a small red dwarf with about 16% of the Sun's mass and only 0.4% of its luminosity. Like Proxima Centauri, Barnard's star is far too faint to see with the naked eye, requiring a telescope to observe its dim red glow. But what Barnard's star lacks in brightness, it makes up for in motion. Barnard's star holds the record for the largest proper motion of any known star. It moves across the sky faster than any other. Every year, it shifts its apparent position by 10.3 arc seconds, covering an angular distance equivalent to the Moon's diameter in just 180 years. This rapid motion is caused by a combination of the star's proximity to Earth and its high velocity relative to the Sunday. Barnard's star is travelling through space at about 142 kilometers per second, cutting across our line of sight at an angle that maximizes its apparent motion. This swift movement has made Barnard's star a favorite target for astronomers studying stellar kinematics. By tracking its position over decades, researchers can measure its trajectory with extraordinary precision and predict its future path. Currently, Barnard's star is moving closer to the Sunday. In roughly 10,000 years, it will reach its closest approach at about 3.75 light-years, briefly becoming the nearest star to our solar system. After that, it will recede again, eventually passing into the distance as other stars drift closer. The star's high velocity suggests it belongs to the galactic halo rather than the disk, a population of older stars with orbits that carry them steeply through the Milky Way's plane. Halo stars formed early in the galaxy's history and tend to have lower metallicities than younger disk stars, like the Sunday. Spectroscopic analysis confirms that Barnard's star contains relatively few heavy elements, consistent with an age of 7 to 12 billion years, making it significantly older than our 4.6 billion-year-old Sunday. For much of the 20th century, Barnard's star was at the center of a controversial claim. In the 1,960 seconds and 1,970 seconds, astronomer Peter van der Kamp reported detecting periodic wobbles in the star's motion, which he attributed to the gravitational influence of two Jupiter-sized planets. If confirmed, these would have been the first exoplanets ever discovered. However, subsequent observations by other astronomers failed to reproduce van der Kamp's results. Eventually, it became clear that the wobbles were instrumental artifacts caused by adjustments to the telescope rather than real planetary signatures. The claim was discredited, and Barnard's star lost its status as a potential planetary system. Decades later, however, the search resumed with far more sophisticated instruments. In 2018, astronomers using the European Southern Observatory's HARP spectrograph announced the discovery of Barnard's star B, a planet with at least 3.2 times Earth's mass, orbiting the star every 233 days. The planet lies near the inner edge of what might be considered the habitable zone, though Barnard's star's low luminosity means the planet likely receives only about 2% of the energy Earth gets from the Sunday. Surface temperatures are estimated at around minus 170 degrees Celsius, making it a frozen world unless some internal heat source or thick atmosphere provides additional warmth. The discovery was significant not just because of the planet's proximity, but because it demonstrated that even the nearest stars could host worlds that remained undetected for decades. Barnard's star B was found using the radial velocity method, which measures the tiny wobbles induced in a star's motion by an orbiting planet's gravity. The signal was extremely weak. Barnard's star's radial velocity changed by only about 1.2 meters per second due to the planet's pull, roughly the speed of a person walking. Detecting such a subtle effect required years of high-precision measurements and careful analysis to separate the planetary signal from noise and stellar activity. Since then, the existence of Barnard's star B has been called into question. Some studies have suggested the signal might be caused by stellar magnetic activity rather than a planet, as red dwarfs like Barnard's star can produce signals that mimic planetary signatures. The debate remains unresolved, highlighting the difficulty of detecting small planets around active, low-mass stars. Barnard's star is also notable for its flare activity. Like other red dwarfs, it undergoes occasional outbursts of magnetic energy that briefly increase its brightness across the electromagnetic spectrum. These flares are less frequent and less intense than those observed on Proxima Centauri, but they still represent significant releases of energy. One flare detected in 1998 increased the star's luminosity by about 10% in visible light, and far more in X-rays and ultraviolet. Such events would have profound effects on any nearby planets, potentially eroding their atmospheres over time. The Lumen 16 system, brown dwarf binary. In 2013, astronomer Kevin Lumen discovered something remarkable using data from NASA's Wide Field Infrared Survey Explorer, N. Just 6.5 light-years from the Sun, closer than any star system discovered in nearly a century, he found a pair of brown dwarfs orbiting each other. The system, now known as Lumen 16AB, is the third closest stellar system to Earth and the closest brown dwarf binary. Brown dwarfs occupy a strange middle ground between stars and planets. They form like stars, collapsing from clouds of gas and dust, but they never accumulate enough mass to sustain hydrogen fusion in their cores. Without fusion, they don't shine like true stars. Instead, they glow faintly from the heat left over from their formation and from the slow fusion of deuterium, a heavy isotope of hydrogen that ignites at lower temperatures. Brown dwarfs are sometimes called failed stars. Though that term is misleading, they're not broken or incomplete, just a different kind of object governed by different physics. Lumen 16AB consists of two brown dwarfs, designated Lumen 16A and Lumen 16B. Lumen 16A is the more massive of the two, with about 34 times the mass of Jupiter, just below the minimum mass needed to sustain hydrogen fusion, which occurs around 75 Jupiter masses. Lumen 16b is slightly less massive at about 28 Jupiter masses. Despite their size, both objects are remarkably small, only slightly larger in radius than Jupiter itself. This is a characteristic feature of brown dwarfs. As they gain mass, they compress under their own gravity, and their radii change very little across a wide range of masses. The two brown dwarfs orbit each other every 27 years at an average distance of about 3.5 astronomical units, roughly the distance between the Sun and the asteroid belt. This close binary configuration makes them ideal targets for studying brown dwarf properties, as astronomers can measure their orbital motions and use them to determine the system's total mass. Both Lumen 16A and Lumen 16b are classified as L-type brown dwarfs, with surface temperatures between 1,300 and 1,500 Kelvin, cooler than the coolest red dwarfs, but hotter than most planets. At these temperatures, their atmospheres are dominated by molecules and dust clouds, rather than the ionized plasmas that characterize true stars. Spectroscopy reveals the presence of water vapor, methane, and metal hydrides, along with silicate clouds that form and dissipate in the turbulent atmospheres. One of the most intriguing aspects of the Lumen 16 system is the variability of Lumen 16b. Observations show that its brightness fluctuates by as much as 10% over periods of a few hours. These variations are thought to be caused by rotating cloud patterns in the atmosphere, similar to Jupiter's bands and storms, but on a far larger and hotter scale. By tracking these brightness changes, astronomers can measure the brown dwarf's rotation period, which turns out to be about 5 hours. This rapid spin distorts the brown dwarf's shape, causing it to bulge at the equator. The Lumen 16 system is so close that it offers unique opportunities for detailed study. In 2014, astronomers used very long baseline interferometry to create the first weather map of a brown dwarf's atmosphere. By combining radio observations from multiple telescopes around the world, they resolved features in Lumen 16b's atmosphere and tracked how cloud patterns moved across its surface. The map revealed large-scale circulation patterns driven by temperature differences and rotation, similar to the jet streams and weather systems on Earth, but far more extreme. Despite extensive searches, no planets have been detected around either lumen 16a or lumen 16b. This isn't surprising. Brown dwarfs have much less mass than stars, and their formation may not produce the same kinds of disks that give rise to planetary systems. However, it's possible that small planets, or even other brown dwarfs, orbit at greater distances beyond the reach of current detection methods. The discovery of the lumen 16 system so close to Earth highlights how much remains unknown about the solar neighbourhood. Despite being one of our nearest neighbours, the system went undetected for decades because brown dwarfs are so faint in visible light. Only infrared surveys like WISE, which observe the heat glow of warm objects, could reveal their presence. This suggests that other nearby brown dwarfs, or even rogue planets, may still be lurking undiscovered in the darkness. Wolf 359, the flaring red dwarf. Wolf 359 is a small, faint red dwarf located just 86 light-years from the Sun in the constellation Leo. It's one of the faintest stars visible from Earth, with an apparent magnitude of 13.5, far too dim to see without a telescope, despite its proximity. Wolf 359 contains only about 9% of the Sun's mass, placing it near the lower limit for sustaining hydrogen fusion. Its surface temperature is around 2,800 Kelvin, and it emits most of its energy in the infrared spectrum. Despite its diminutive size, Wolf 359 is remarkably active, undergoing frequent and powerful stellar flares. Red dwarfs, like Wolf 359, are magnetically active stars. Their interiors convect vigorously, with hot plasma rising to the surface and cooler material sinking inward. This convection generates powerful magnetic fields that twist and tangle, occasionally releasing stored energy in sudden bursts called flares. During a flare, the star's brightness can increase dramatically, sometimes by several magnitudes in visible light, and even more in X-rays and ultraviolet radiation. These outbursts last anywhere from minutes to hours and release energy equivalent to millions of hydrogen bombs exploding simultaneously. Wolf 359 is classified as a flare star, a category of red dwarfs known for their frequent and violent eruptions. Observations have recorded multiple flares from the star, some increasing its luminosity by more than a factor of 5. These events are driven by magnetic reconnection, the sudden rearrangement of magnetic field lines that releases enormous amounts of stored energy. The process is similar to solar flares on the Sun, but Wolf 359's flares are far more intense relative to the star's baseline luminosity. The implications for any potential planets around Wolf 359 are significant. Flares release not just visible light, but also X-rays and charged particles that can strip away planetary atmospheres if the planet lacks a strong magnetic field. For a planet orbiting in the habitable zone of a red dwarf, this radiation environment could be particularly harsh, as the habitable zone lies much closer to the star than it does around Sun-like stars. Wolf 359's habitable zone would be located at about 0.04 astronomical units, only 10% of Mercury's distance from the Sunday. At such close range, any planet would be tidally locked, with one side permanently facing the star, and would be subjected to intense flare activity. Despite extensive searches, no planets have been confirmed around Wolf 359. The star's high magnetic activity complicates detection efforts, as flares and star spots can mimic or obscure the signals of orbiting planets. Radial velocity measurements, which rely on detecting the star's wobble caused by a planet's gravity, are particularly challenging because stellar activity introduces noise into the data. Transit searches are similarly difficult, as the star's variability makes it hard to identify the shallow dips in brightness caused by a planet crossing in front of the star. Wolf 359 is also notable for its high proper motion. It moves across the sky at about 4.7 arcseconds per year, one of the faster proper motions among nearby stars. This motion is caused by the star's velocity relative to the Sun, estimated at about 19 kilometers per second. Unlike Barnard's star, which is approaching the Sun, Wolf 359 is moving away and will gradually become more distant over the coming millennia. Spectroscopic studies reveal that Wolf 359 has a low metallicity compared to the Sun, with only about 18% of the solar abundance of heavy elements. This suggests the star formed from gas that had been enriched by relatively few generations of earlier stars. Low metallicity is common among red dwarfs, many of which formed early in the galaxy's history when the interstellar medium contained fewer heavy elements. The star's age is estimated at several billion years, though precise ages for red dwarfs are notoriously difficult to determine because they evolve so slowly. Wolf 359 has also served as a reference object for astrometry and parallax measurements. Its proximity and relatively high proper motion make it an excellent target for testing the precision of new instruments. Observations from Hipparcos, Gaia, and ground-based telescopes have refined its distance and motion to high accuracy, contributing to our understanding of the structure and dynamics of the local stellar neighborhood. The star's flare activity has been studied extensively by space telescopes like TESS Transiting Exoplanet Survey Satellite and SWIFT, which observe in ultraviolet and X-ray wavelengths where flares are most prominent. These observations have revealed that Wolf 359 undergoes flares at least once every few days, with some lasting several hours. The energy released during these events is substantial, equivalent to a significant fraction of the star's total luminosity over short timescales. Sirius, the brightest star in Earth's sky. At a distance of 8.6 light-years, Sirius is the fifth closest star system to the Sun, and by far the brightest star visible from Earth. On clear winter nights in the northern hemisphere, it dominates the southeastern sky, shining with a dazzling blue-white light that has captivated observers for millennia. The ancient Egyptians based their calendar on the heliacal rising of Sirius, which coincided with the annual flooding of the Nile. The Greeks called it the Dog Star, as it forms the nose of Canis Major, the Great Dog constellation. Sirius is actually a binary system consisting of two stars, Sirius A, a brilliant main sequence star, and Sirius B, a faint white dwarf companion. Sirius A is about twice the mass of the Sun and 25 times as luminous. It belongs to the spectral class A1V, indicating a hot hydrogen-burning star with a surface temperature of around 9,940 Kelvin. This high temperature gives Sirius its characteristic blue-white colour. The star rotates rapidly, completing one rotation in about 16 hours, far faster than the Sun's 25-day rotation period. This rapid spin creates a flattened, oblate shape, with the equatorial radius slightly larger than the polar radius. Sirius B, the companion star, is one of the nearest and most studied white dwarfs. White dwarfs are the remnants of stars that have exhausted their nuclear fuel and shed their outer layers, leaving behind a dense core composed mostly of carbon and oxygen. Sirius B contains roughly the mass of the Sun compressed into a volume only slightly larger than Earth. This extreme density, about 1 million times that of water, means a teaspoon of white dwarf material would weigh several tons. Despite its mass, Sirius B is about 10,000 times fainter than Sirius A, making it difficult to observe directly. The two stars orbit each other every 50.1 years at distances ranging from 8 to 31 astronomical units, comparable to the distance between the Sun and Uranus. The orbital parameters have been measured with high precision through astrometry, allowing astronomers to calculate the masses of both stars using Kepler's laws. Sirius A weighs in at 2.06 solar masses, while Sirius B contains about 1.02 solar masses, remarkably close to the Sun's mass, but packed into a much smaller volume. The discovery of Sirius B is a fascinating story in the history of astronomy. In 1844, German astronomer Friedrich Bessel noticed that Sirius exhibited a slight wobble in its proper motion, as if being tugged by an unseen companion. He correctly deduced that Sirius must be part of a binary system, with the companion's gravity causing the visible star to oscillate. Nearly 20 years later, in 1862, American telescope maker Alvan Graham Clark spotted Sirius B for the first time while testing a new refracting telescope. The discovery confirmed Bessel's prediction and provided the first evidence that stars could exist in binary systems where one component was far fainter than the other. Sirius B's nature remained mysterious until the early 20th century. Spectroscopic observations revealed it was extremely hot, about 25,000 Kelvin, yet far too faint to be a normal main-sequence star. Applying the Stefan-Boltzmann law, which relates luminosity to surface temperature and radius, astronomers realized the star must be extraordinarily small. This conclusion led to the recognition that white dwarfs represent a new class of stellar objects, with densities far exceeding anything previously imagined. The study of Sirius B played a crucial role in the development of stellar evolution theory. In the 1920 seconds, British astrophysicist Arthur Eddington proposed that white dwarfs were held up by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being compressed beyond a certain density. This idea was formalized by Subramanian Chandrasekhar in the 1930 seconds, who showed that white dwarfs have a maximum mass limit about 1.4 solar masses, beyond which they collapse into neutron stars or black holes. Sirius B, with its mass just over 1 solar mass, sits comfortably below this limit and will remain a white dwarf indefinitely, slowly cooling and fading over trillions of years. Sirius A, meanwhile, remains a vibrant main-sequence star, fusing hydrogen into helium in its core. Given its mass and age, estimated at around 200 to 300 million years, Sirius A will continue burning for several hundred million more years before exhausting its core hydrogen. When that happens, it will expand into a red giant, eventually shedding its outer layers and leaving behind another white dwarf. At that point, the Sirius system will consist of 2 white dwarfs, slowly cooling together in the darkness. The Sirius system has no confirmed planets, despite extensive searches. Given the system's youth and the violent evolution Sirius B underwent as it swelled into a red giant and then shed its envelope, any planets that once existed may have been destroyed or ejected. However, the possibility of planets around Sirius A cannot be ruled out entirely. Future observations with more sensitive instruments may reveal whether this nearby system hosts any worlds. Ross 154, the silent red dwarf. Ross 154 is a faint red dwarf located 9.69 light-years from the Sun in the constellation Sagittarius. Discovered in 1925 by American astronomer Frank Elmore Ross during a photographic survey, it's one of several dozen stars named after him. Ross 154 is classified as an M3 5-volt star, indicating a cool, low-mass, main-sequence red dwarf. With only about 17% of the Sun's mass and a surface temperature around 3,200 Kelvin. It emits most of its light in the infrared spectrum and is far too faint to see with the naked eye, requiring a telescope for observation. Despite its proximity, Ross 154 has drawn less scientific attention than some of its more active neighbours, like Proxima Centauri or Wolf 359. This is largely because Ross 154 is relatively quiet compared to other red dwarfs. While most red dwarfs are prone to frequent flares, sudden eruptions of magnetic energy that temporarily increase their brightness, Ross 154 exhibits very little flare activity. This makes it a more stable star, but also less interesting for studies of stellar magnetism and activity. The star's low activity level may be related to its rotation rate. Red dwarfs generate magnetic fields through convection in their interiors, and faster rotation tends to produce stronger magnetic fields and more frequent flares. Ross 154 rotates relatively slowly for a red dwarf, with a rotation period estimated at several weeks. This slow spin reduces the efficiency of its magnetic dynamo, resulting in weaker fields and fewer flares. In this sense, Ross 154 represents the quieter end of the red dwarf spectrum, a star that has settled into a more sedate middle age. Ross 154's motion through space is notable. It has a high proper motion of about 0.67 arc-seconds per year, caused by its velocity relative to the Sunday. The star is moving closer to us at a rate of about 10 kilometers per second. In approximately 150,000 years, it will reach its closest approach at about 6.4 light-years, temporarily becoming the third closest star system to the Sunday. After that, it will recede again, continuing on its long journey through the galaxy. Spectroscopic analysis reveals that Ross 154 has a metallicity roughly half that of the Sun, suggesting it formed from gas that had been less enriched by previous generations of stars. This lower metallicity is common among red dwarfs, which tend to be older on average than Sun-like stars. Ross 154's age is difficult to determine. Precisely, red dwarfs evolve so slowly that stars of vastly different ages can appear nearly identical, but estimates place it at several billion years old. No planets have been detected around Ross 154, despite searches using radial velocity and transit methods. Given the star's low activity, it's an excellent candidate for planet detection, as the lack of flares and star spots reduces the noise in observational data. However, the absence of detected planets doesn't necessarily mean they don't exist. Small, low-mass planets could easily remain hidden below current detection thresholds, especially if they orbit at distances that produce weak signals. Ross 154's relatively quiet nature has made it a reference object for studies comparing active and inactive red dwarfs. By examining stars across the spectrum of magnetic activity, astronomers can better understand the factors that control stellar magnetism and how it evolves over a star's lifetime. Stars like Ross 154, with their low flare rates and slow rotations, provide a contrast to the violent activity seen on stars like Proxima Centauri and Wolf 359. The star has also been used in studies of stellar kinematics. By tracking its motion through space and comparing it to other nearby stars, astronomers can map the structure and dynamics of the local stellar neighbourhood. Ross 154's trajectory suggests it belongs to the thin disk population of the galaxy stars that orbit in the galactic plane with relatively low velocities perpendicular to the disk. This is consistent with its moderately low metallicity and estimated age. Infrared observations have provided detailed information about Ross 154's spectrum revealing absorption lines from molecules like titanium oxide and water vapor, which are common in the cool atmospheres of red dwarfs. These molecules form because the star's surface temperature is low enough for certain chemical bonds to remain stable. In hotter stars, these molecules would be broken apart by intense radiation, but on red dwarfs, they contribute to the star's overall opacity and influence how energy escapes from the surface. Ross 154's luminosity is only about 0.4% that of the Sun, meaning it emits about 250 times less energy. Despite this faintness, red dwarfs like Ross 154 are the most energy-efficient stars in the universe. They burn hydrogen so slowly that they can remain on the main sequence for trillions of years, far longer than the current age of the universe. While massive stars like Sirius A will exhaust their fuel within a few 100 million years, Ross 154 will continue shining long after the Sun has died, becoming one of the last stars left burning in a cold, dark cosmos. The Y0855-0714 system, the coldest known brown dwarf. In 2014, astronomers analyzing data from NASA's WISE infrared space telescope discovered one of the strangest objects in the solar neighborhood, Y08550714, a brown dwarf so cold and faint that it borders on being planet-like. Located just 7.27 light-years from the Sun, it's the fourth closest known system and the coldest brown dwarf ever detected, with a temperature estimated at around 225 Kelvin, about minus 48 degrees Celsius. This makes it colder than the coldest temperature ever recorded on Earth, and even colder than some of the outer planets in our solar system. WISE 08550714 challenges traditional definitions of stars and planets. With an estimated mass between 3 and 10 times that of Jupiter, it falls into the category of brown dwarfs, objects too massive to be planets, but too small to sustain hydrogen fusion. However, unlike warmer brown dwarfs that glow visibly in infrared light, Y0855 is so cold that it emits almost no detectable radiation. It's invisible to ordinary telescopes and can only be seen in mid-infrared wavelengths, where it appears as a faint, point-like source barely distinguishable from the background sky. The discovery of Y0855 was possible only because of WISE's sensitivity to faint infrared sources. WISE mapped the entire sky in 4 infrared wavelengths, cataloguing hundreds of millions of objects. Among them were several previously unknown brown dwarfs, and even free-floating planets objects that wander through space unbound to any star. WISE 0855 stood out because of its extreme faintness and cold temperature, making it one of the most significant finds from the mission. At such low temperatures, WISE 0855's atmosphere is dominated by water clouds, not vapor, but actual clouds of water ice particles, similar to those found in Earth's atmosphere, but in a much colder environment. Spectroscopic observations using powerful ground-based telescopes like Gemini North have detected the signature of water absorption in the brown dwarf spectrum, confirming the presence of these clouds. This makes WISE 0855 one of the few objects outside our solar system where weather phenomena resembling Earth's have been observed. The coldest brown dwarfs, like WISE 0855, are classified as Y-type dwarfs, the coolest spectral class. Y dwarfs have temperatures below 500 Kelvin and exhibit spectroscopic features dominated by ammonia and water, similar to gas giant planets like Jupiter and Saturn. In fact, WISE 0855's atmosphere may closely resemble that of Jupiter, with cloud layers at different altitudes and complex chemical processes driven by temperature gradients. Studying such objects provides insights into planetary atmospheres without the complications introduced by starlight. WISE 0855's extreme coldness also raises questions about its formation and evolution. Brown dwarfs form like stars, collapsing from clouds of gas and dust. However, because they never ignite hydrogen fusion, they have no long-term energy source and gradually cool over billions of years. WISE 0855 has likely been cooling for several billion years, radiating away the heat left over from its formation. Its current temperature suggests it's relatively old, though precise age estimates are difficult without additional data. The brown dwarf's motion through space has been measured with high precision. It has a proper motion of about 8.1 arc-seconds per year, one of the largest among nearby objects, indicating a high velocity relative to the Sunday. This motion is consistent with WISE 0855, being an old halo object, a member of the population of ancient stars and brown dwarfs that formed early in the galaxy's history and now move through the Milky Way on elongated orbits. No planets have been detected around WISE 0855, and given its low mass and cold temperature, it's unclear whether it could host a planetary system. Brown dwarfs this small may not form the kinds of disks necessary for planet formation, or any planets that did form may have drifted away over billions of years. However, the possibility of even colder, more planet-like objects orbiting WISE 0855 cannot be entirely ruled out. The discovery of WISE 0855 suggests that the solar neighbourhood may contain many more such objects waiting to be found. Cold brown dwarfs and free-floating planets are extremely difficult to detect because they emit so little light. Even nearby, they remain invisible to most surveys. Future missions with greater sensitivity in the infrared, such as the James Webb Space Telescope and the Nancy Grace Roman Space Telescope, may uncover a population of ultra-cool dwarfs and rogue planets that have so far eluded detection. Epsilon Eridani, a young sun with a debris disk. Epsilon Eridani is one of the most intriguing stars in the solar neighbourhood. Located 10.48 light-years from the Sun in the constellation Eridanus. It's a K-type main-sequence star slightly smaller and cooler than the Sun, with about 82% of the Sun's mass and a surface temperature around 5,000 Kelvin. What makes Epsilon Eridani particularly interesting is its youth at roughly 800 million years old. It's much younger than our 4.6 billion-year-old Sunday. This makes it an excellent analogue for studying what our solar system may have looked like during its early, turbulent history. Epsilon Eridani is surrounded by a prominent debris disk, a ring of dust and rocky material, orbiting the star at distances ranging from about 35 to 90 astronomical units. Debris disks are remnants of planet formation, consisting of leftover material that never coalesced into planets, along with dust produced by collisions between asteroids and comets. Epsilon Eridani's disk is particularly dense and well studied, emitting strong infrared radiation detected by space telescopes like Spitzer and Herschel. The structure of the debris disk suggests the presence of planets. Gravitational interactions with orbiting planets can sculpt debris disks into rings and gaps, concentrating dust at certain distances while clearing it from others. Observations of Epsilon Eridani's disk reveal asymmetries and clumps that hint at the influence of unseen planets stirring the material. These features are similar to those seen in our own solar system, where Neptune's gravity shapes the Kuiper belt, and Jupiter's influence creates gaps in the asteroid belt. In 2000, astronomers announced the discovery of Epsilon Eridani b, a gas giant planet with at least 1.5 times Jupiter's mass, orbiting the star every 7.4 years at a distance of about 3.4 astronomical units. The planet was detected using the radial velocity method, which measures the wobble induced in the star's motion by the planet's gravity. Epsilon Eridani b is one of the closest known exoplanets and has been studied extensively since its discovery. However, the existence and properties of Epsilon Eridani b remain uncertain. Follow-up observations have produced conflicting results, with some studies supporting the planet's existence and others suggesting the signal may be caused by stellar activity rather than a planet. Red dwarfs and young stars, like Epsilon Eridani, often exhibit magnetic activity that can mimic planetary signals, complicating detection efforts. Additional observations with more advanced instruments are needed to confirm the planet definitively. Beyond Epsilon Eridani b, there's evidence for additional planets in the system. Some models of the debris disk structure suggest the presence of a second planet farther out, possibly a Neptune-like ice giant that helps confine the inner edge of the disk. However, no direct detection of such a planet has been made, and its existence remains speculative. Epsilon Eridani's youth and high activity level make it a challenging target for planet detection. The star rotates relatively quickly, with a rotation period of about 11 days, and exhibits frequent star spots, cool, dark regions on the surface caused by intense magnetic fields. These spots come and go as the star rotates, causing periodic variations in brightness and spectroscopic signals that can be mistaken for planetary transits or radial velocity wobbles. Distinguishing real planetary signals from stellar noise requires careful analysis and long-term monitoring. The star's high level of magnetic activity also manifests in X-ray and ultraviolet emission. Young stars like Epsilon Eridani are far more active than older stars because they haven't yet spun down through magnetic braking, a process in which stellar winds carry away angular momentum, gradually slowing the star's rotation. As Epsilon Eridani ages, its rotation will slow, its magnetic fields will weaken, and its activity will decline. In a few billion years, it may resemble the Sun as we know it today. Epsilon Eridani's proximity and Sun-like characteristics have made it a popular target in the search for extraterrestrial intelligence. The star has been observed multiple times by radio telescopes searching for signals from advanced civilizations, though no confirmed detections have been made. Its relative youth raises the question of whether life could have emerged on any planets in the system. To 800 million years is far less time than Earth needed to develop complex life, but it's conceivable that simpler organisms could exist. Lacaille 9352, the southern red dwarf. Lacaille 9352 is a faint red dwarf located 10.69 light-years from the Sun in the constellation Piscis Austrinus. Discovered by French astronomer Nicolas Louis de Lacaille during his 18th century survey of the southern skies, it's one of the nearest stars to Earth and one of the brightest red dwarfs visible from the southern hemisphere. Despite its proximity, Lacaille 9352 is far too faint to see with the naked eye, requiring at least binoculars or a small telescope to observe. Classified as an M1 5-volt star, Lacaille 9352 has about 51% of the Sun's mass and a surface temperature around 3600 Kelvin. It's somewhat larger and hotter than many nearby red dwarfs, placing it near the upper end of the M-dwarf spectrum. With a luminosity roughly 1.4% that of the Sun, it emits far less energy but remains significantly brighter than ultra-cool dwarfs like Proxima Centauri or WISE 0855. One of Lacaille 9352's most notable features is its high proper motion. It moves across the sky at about 6.9 arc seconds per year. one of the fastest apparent motions of any star. This rapid motion is caused by the star's velocity relative to the Sun, estimated at about 30 kilometers per second. Lacaille 9352 is currently moving closer to the Sun, and in approximately 19,000 years, it will reach its closest approach at about 8.1 light-years before receding again. The star's kinematics suggest it belongs to the thin disk population of the Milky Way, meaning it orbits in the galactic plane with relatively low velocity perpendicular to the disk. Spectroscopic analysis reveals a metallicity about 60% that of the Sun, indicating it formed from gas enriched by previous generations of stars, but not as much as younger metal-rich stars like the Sunday. Lacaille 9352 exhibits moderate magnetic activity, with occasional flares and star spots detected in photometric and spectroscopic observations. While not as active as the most violent flare stars, it shows more variability than quiet red dwarfs like Ross 154. This intermediate level of activity makes it an interesting target for studying how stellar magnetism varies across the red dwarf population. No planets have been confirmed around Lacaille 9352. Though searches are ongoing, the star's relative brightness compared to other red dwarfs makes it a favourable target for radial velocity and transit surveys. If planets exist, they could potentially be detected with current or near-future instruments. Given the star's age, estimated at several billion years, any planetary system would have had ample time to stabilise, making it a potentially hospitable environment for planets. Lacaille 9352 has been observed extensively as part of parallax and proper motion studies. Its proximity and high apparent motion make it an excellent reference for testing astrometric instruments and techniques. Data from Hipparcos and Gaia have refined its distance and motion to high precision, contributing to our understanding of the structure and kinematics of the local stellar neighbourhood. The star's location in the southern sky has made it a popular target for astronomers in the southern hemisphere. Several observatories in Chile, Australia, and South Africa have monitored Lacaille 9352 over the years, accumulating decades of photometric and spectroscopic data. This long observational baseline has allowed researchers to track subtle changes in the star's activity and motion, providing insights into the long-term behaviour of red dwarfs. Lacaille 9352's spectrum shows strong absorption lines from molecules like titanium oxide, which are characteristic of cool M-dwarf atmospheres. These molecular bands form because the star's surface temperature is low enough for molecules to remain stable. In hotter stars, these molecules would be dissociated by intense radiation. But on red dwarfs, they play a significant role in the star's opacity and energy transport. Ross 128, the quiet neighbour. Ross 128 is a red dwarf located 11.03 light-years from the Sun in the constellation Virgo. Discovered in 1926 by Frank Elmore Ross, it's one of several nearby red dwarfs that have become important targets in the search for exoplanets. Ross 128 is classified as an M4V star, indicating a cool, low-mass red dwarf with about 17% of the Sun's mass and a surface temperature around 3,200 Kelvin. What sets Ross 128 apart from many other red dwarfs is its remarkable quietness. Unlike stars like Proxima Centauri or Wolf 359, which undergo frequent and violent flares, Ross 128 exhibits very little magnetic activity. It's classified as an inactive red dwarf, with rotation periods estimated at over 100 days far slower than most stars of its type. This slow rotation reduces the efficiency of its magnetic dynamo, resulting in weak magnetic fields and minimal flare activity. This lack of activity makes Ross 128 an ideal host for potentially habitable planets. Frequent flares can strip away planetary atmospheres and bombard surfaces with harmful radiation, making life unlikely on planets around active red dwarfs. Ross 128's quiet nature eliminates much of this concern, making any planets in its habitable zone more likely to retain atmospheres and maintain stable climates over long timescales. In 2017, astronomers announced the discovery of Ross 128b, a planet with at least 1.35 times Earth's mass orbiting the star every 9.9 days. The planet was detected using the HARP spectrograph at the European Southern Observatory's La Silla facility in Chile, which measured the tiny wobbles induced in Ross 128's motion by the planet's gravity. Ross 128b orbits at a distance of about 0.05 astronomical units, only 5% of the distance between Earth and the Sun, placing it well within what would be the habitable zone around a Sun-like star. However, because Ross 128 is much cooler and less luminous than the Sun, the habitable zone lies much closer to the star. At its orbital distance, Ross 128b receives about 1.38 times the energy Earth gets from the Sun, placing it near the inner edge of the habitable zone. Surface temperatures are estimated to range between -60 and +20 degrees Celsius, depending on the planet's atmosphere and albedo. If Ross 128b has an atmosphere similar to Earth's, temperatures could be warm enough to support liquid water on the surface. The planet is likely tidally locked, with one side permanently facing the star and the other in eternal darkness. This is a common outcome for planets orbiting close to their stars, as tidal forces synchronize the planet's rotation period with its orbital period over time. Tidally locked planets can still be habitable if their atmospheres are thick enough to transport heat from the day side to the night side, preventing extreme temperature gradients. Ross 128b is one of the closest known potentially habitable exoplanets, making it a prime target for future atmospheric studies. The James Webb Space Telescope and upcoming extremely large telescopes will be able to analyze the planet's atmosphere by observing how starlight filters through it during transits if the planet's orbit is aligned favorably. Detecting molecules like water vapor, oxygen, or methane could provide clues about the planet's climate and even the possibility of life. Ross 128's proximity and low activity level make it an excellent candidate for future interstellar missions. At just over 11 light-years away, it's close enough that a spacecraft traveling at 10% of the speed of light could reach it in about 110 years. While such speeds remain far beyond current technology, concepts like laser-driven light sails have been proposed as potential pathways to interstellar travel. Ross 128b could be among the first exoplanets visited by humanity's robotic emissaries. The star's motion through space is also noteworthy. Ross 128 has a high proper motion of about 1.4 arcseconds per year and is moving closer to the Sun at a velocity of about 11 kilometers per second. In approximately 79,000 years, it will pass within 6.4 light-years of the Sun, temporarily becoming one of our closest stellar neighbours. This approach will make Ross 128 and its planet even more accessible for study and exploration. Spectroscopic observations reveal that Ross 128 has a metallicity about 40% that of the Sun, suggesting it formed from gas less enriched by previous stellar generations. This lower metallicity is typical of older red dwarfs, though precise age estimates are difficult to determine. The star's low activity and slow rotation suggest it's relatively old, possibly several billion years, though it could continue shining for trillions more years. EZ Aquarii, the triple red dwarf system. EZ Aquarii is a remarkable triple star system located 11.27 light-years from the Sun in the constellation Aquarius. All 3 stars in the system are red dwarfs, making it one of the few nearby systems composed entirely of low-mass stars. The system consists of a close binary pair, EZ Aquarii A and B, orbited by a more distant third component, EZ Aquarii C. The entire system offers a fascinating laboratory for studying stellar dynamics, magnetic activity, and the behavior of close orbiting red dwarfs. EZ Aquarii A, the most massive of the 3, has about 11% of the Sun's mass, while EZ Aquarii B weighs in at around 11% as well. The 2 stars orbit each other every 3.8 days at a separation of only 0.03 astronomical units, about 4.5 million kilometers, or roughly 6 times the radius of the Sunday. This extreme proximity means the stars are gravitationally locked, with each presenting the same face to its companion at all times, similar to how the Moon is tidally locked to Earth. The third component, EZ Aquarii C, is slightly less massive at about 10% of the Sun's mass. It orbits the close binary at a distance of about 5.5 astronomical units, completing one orbit every 14 years. This hierarchical configuration, a tight binary with a distant companion, is common among multiple star systems and remains stable over long timescales, as long as the distances and masses fall within certain ratios. All 3 stars in the EZ Aquarii system are classified as M-type red dwarfs, with surface temperatures around 3000 Kelvin. Despite their small sizes, all 3 exhibit significant magnetic activity, including flares and star spots. This activity is driven by rapid rotation and convective motions in their interiors, which generate powerful magnetic fields. EZ Aquarii A and B, locked in their tight embrace, rotate synchronously with their 3-8-day orbital period, while EZ Aquarii C rotates independently. The close binary pair is particularly interesting because their proximity intensifies tidal interactions, which in turn affect their magnetic activity. Studies have shown that the binary components undergo coordinated flares on simultaneous eruptions on both stars, suggesting their magnetic fields are linked or influenced by their mutual proximity. This kind of magnetic interaction is rare and provides insights into how stellar magnetism behaves in extreme environments. No planets have been detected around EZ Aquarii, and the system's complex dynamics make planet formation and stability challenging. In the close binary, tidal forces and gravitational perturbations would likely disrupt any forming protoplanetary disk, preventing planets from coalescing. Around EZ Aquarii C, planets might be more stable, but they would still experience gravitational perturbations from the binary pair, leading to eccentric orbits or ejection over time. However, circumbinary planets, worlds that orbit both members of a binary system, are theoretically possible and have been discovered around other binary stars. In the case of EZ Aquarii, a circumbinary planet would need to orbit well beyond the close binary, at distances where its orbit remains stable despite the gravitational influence of both stars. Such planets, if they exist, remain undetected with current observational techniques. EZ Aquarii's proximity makes it a valuable target for studies of red dwarf properties and multiplicity. Multiple star systems are common in the galaxy. More than half of all stars are thought to belong to binary or higher order systems, and understanding how these systems form and evolve provides insights into star formation processes. EZ Aquarii, with its 3 low-mass components, represents a common configuration that may be widespread throughout the Milky Way, but difficult to detect at greater distances due to the faintness of red dwarfs. The system's kinematics have been measured with high precision. EZ Aquarii has a proper motion of about 3.3 arcseconds per year and is moving away from the Sun at a velocity of about 7 kilometers per second. Over the coming millennia, it will gradually recede, becoming more distant and even fainter. Spectroscopic studies reveal that all 3 stars have low metallicities, roughly 30 to 40% that of the Sunday. This suggests the system formed from gas that had been less enriched by previous stellar generations, consistent with an age of several billion years. Despite this age, the stars remain highly active, demonstrating that red dwarfs can maintain strong magnetic fields and flare activity for billions of years, far longer than Sun-like stars. 61 Cygni, the historic binary. 61 Cygni is a binary star system located 11.4 light-years from the Sun in the constellation Cygnus. It holds a special place in the history of astronomy as the first star to have its distance measured through stellar parallax, a milestone achievement that opened the door to understanding the true scale of the universe. The system consists of 2 K-type orange dwarf stars, designated 61 Cygni A and 61 Cygni B, orbiting each other every 659 years. In 1838, German astronomer Friedrich Wilhelm Bessel succeeded in measuring 61 Cygni's parallax using a heliometer, an instrument designed to measure small angular separations. He detected a parallax angle of 0.314 arcseconds, corresponding to a distance of about 10.3 light-years, remarkably close to the modern value of 11.4 light-years. This measurement provided the first direct proof of Earth's motion around the Sun and revealed that the stars are vastly more distant than anyone had imagined. For this achievement, 61 Cygni is sometimes called the flying star, due to its rapid, proper motion, which Bessel used to select it as a target. 61 Cygni has the 5th largest proper motion of any star visible to the naked eye, moving across the sky at about 5.2 arcseconds per year. This rapid motion is caused by its high velocity relative to the Sun, about 108 kilometers per second, combined with its proximity. The star's trajectory carries it through the Milky Way's disk at an angle, and it's currently moving away from the Sun, though only slightly. The 2 components of the system are similar in many respects. 61 Cygni A has about 70% of the Sun's mass and a surface temperature around 4,500 Kelvin, while 61 Cygni B is slightly smaller and cooler, with about 63% of the Sun's mass and a temperature of 4,200 Kelvin. Both stars are main sequence dwarfs, fusing hydrogen into helium in their cores, and both will continue doing so for billions of years. The 2 stars orbit each other at an average distance of about 84 astronomical units, roughly twice the distance between the Sun and Pluto. Their orbital period of 659 years means that even over the span of a human lifetime, their relative positions change only slightly. Observations over the past 2 centuries have traced out a small portion of their elliptical orbit, allowing astronomers to calculate their masses using Kepler's laws. 61 Cygni has been a subject of intense interest in the search for exoplanets. In the 1,940 seconds and 1,950 seconds, astronomer Kai Strand claimed to have detected perturbations in the star's orbits caused by unseen planetary companions. He proposed the existence of a planet with about 8 times Jupiter's mass orbiting 61 Cygni A. However, subsequent observations failed to confirm these perturbations, and the planet claim was eventually discredited. The supposed signals were likely artifacts of instrumental errors or misinterpretations of the data. Despite this false start, searches for planets around 61 Cygni have continued. Modern radial velocity and astrometric surveys have so far found no evidence of massive planets, though smaller, Earth-sized worlds could still exist below current detection limits. The system's age, estimated at around 6 billion years, would have given any planets ample time to form and stabilize, making it a plausible host for a planetary system. Both stars in the 61 Cygni system exhibit moderate magnetic activity, including star spots and flares, though less intense than the activity seen on red dwarfs. Their rotation periods are around 38 days for 61 Cygni A and 40 days for 61 Cygni B, slower than young stars, but faster than the Sun's 25-day rotation. This suggests the stars are middle-aged and have undergone some magnetic braking, though they haven't yet reached the quiet, slow rotating phase seen in older stars. Spectroscopic studies reveal that both stars have metallicities about 40% that of the Sun, indicating they formed from gas less enriched by previous stellar generations. This lower metallicity is consistent with their age and kinematics, which suggests they belong to the thick disk population of the Milky Way stars that formed early in the galaxy's history and now orbit with higher velocities and more eccentric paths than younger thin disk stars like the Sunday. 61 Cygni's historical significance and proximity have made it a frequent target for astronomical observations. Ground-based telescopes, space observatories like Hipparcos and Gaia, and even amateur astronomers have monitored the system over the decades. Its motion through space has been tracked with high precision, contributing to studies of stellar kinematics and the structure of the solar neighborhood. Procyon, the little dog star. Procyon is the 8th closest star system to the Sun, located 11.46 light-years away in the constellation Canis Minor, the little dog. It's one of the brightest stars in the night sky and forms one vertex of the winter triangle, an asterism visible from the northern hemisphere during winter months, along with Sirius and Betelgeuse. Like Sirius, Procyon is a binary system consisting of a bright main sequence star, Procyon A, and a faint white dwarf companion, Procyon B. Procyon A is an F-type main sequence star with about 1.5 times the Sun's mass and roughly 7 times its luminosity. It has a surface temperature of approximately 6,500 Kelvin, giving it a yellowish-white colour slightly hotter than the Sunday. The star is nearing the end of its main sequence lifetime and will soon begin evolving into a subgiant as it exhausts the hydrogen in its core. Over the next few million years, Procyon A will expand and cool, eventually shedding its outer layers to form a planetary nebula and leaving behind a white dwarf remnant similar to Procyon B. Procyon B, the white dwarf companion, is one of the nearest and most studied white dwarfs after Sirius B. It contains about 60% of the Sun's mass compressed into a volume roughly the size of Earth, resulting in a density about 200,000 times that of water. Despite its mass, Procyon B is incredibly faint, with a luminosity only about 0.06% to that of the Sunday. It's invisible to the naked eye and challenging to observe even with telescopes due to the glare from Procyon A. The two stars orbit each other every 40.8 years, at distances ranging from 9 to 21 astronomical units, comparable to the distance between the Sun and Uranus. The orbital parameters have been measured with high precision through astrometry, allowing astronomers to calculate the masses of both stars using Kepler's laws. The existence of Procyon B was predicted before it was observed. In 1844, Friedrich Bessel noticed irregularities in Procyon A's proper motion, suggesting the presence of an unseen companion. This was the same technique he used to predict the existence of Sirius B. However, Procyon B remained undetected for decades due to its extreme faintness. It was finally observed in 1896 by John Martin Schaeberle using the 36-inch refractor at Lick Observatory. Procyon B's discovery confirmed that white dwarfs could exist as companions to normal stars, supporting the emerging theory of stellar evolution. Like Sirius B, Procyon B is extremely hot for its size, with a surface temperature around 7,700 Kelvin. This high temperature, combined with its small radius, places it in the category of white dwarfs that are slowly cooling and fading over billions of years. No planets have been detected around Procyon, though searches are ongoing. The presence of a white dwarf companion suggests that Procyon B once underwent a red giant phase, during which it would have swelled to hundreds of times its original size. This expansion likely destroyed any planets that orbited close to the star, and gravitational interactions during the mass loss phase may have disrupted planets farther out. However, planets around Procyon A, if they exist, might have survived if they orbited at sufficient distances. Procyon A's relatively high mass and luminosity mean it's evolving more rapidly than the Sunday. Its age is estimated at around 1.9 billion years, making it significantly younger than our solar system. Despite this youth, Procyon A is already approaching the end of its hydrogen-burning phase. In astronomical terms, it's a middle-aged star on the verge of old age, soon to undergo the transformations that will ultimately turn it into a white dwarf like its companion. The Procyon system's proximity and brightness have made it a popular target for studies of stellar properties and binary evolution. Its motion through space has been tracked with high precision, revealing a space velocity of about 3 kilometers per second relative to the Sunday. The system is moving slowly through the local stellar neighborhood, neither approaching nor receding rapidly. Spectroscopic analysis reveals that Procyon A has a metallicity slightly higher than the Sun's, about 130% solar abundance. This higher metallicity suggests the star formed from gas enriched by previous generations of stars, consistent with its membership in the thin disk population of the Milky Way. The enhanced metal content may have influenced the star's evolution, affecting its luminosity and lifetime. Struve 2398, the red dwarf binary. Struve 2398 is a binary star system located 11.52 light-years from the Sun in the constellation Draco. Both components are red dwarfs, making it one of the nearest all-red dwarf binaries. The system was catalogued in the 19th century by Russian astronomer Friedrich Georg Wilhelm von Struve, who conducted extensive surveys of double stars. Struve 2398 consists of two M-type red dwarfs, designated Struve 2398A and Struve 2398B, orbiting each other every 295 years. Struve 2398A is slightly more massive, with about 29% of the Sun's mass and a surface temperature around 3,500 Kelvin. Struve 2398b is somewhat smaller, containing about 26% of the Sun's mass with a similar temperature. Both stars are classified as M3V dwarfs, placing them in the mid-range of red dwarf properties, cooler and less massive than stars like Ross 128, but warmer and more luminous than ultra-cool dwarfs like Proxima Centauri. The two stars orbit at an average separation of about 55 astronomical units, roughly the distance between the Sun and the outer edge of the Kuiper belt. This relatively wide separation means gravitational interactions between the stars are weak, and each maintains its own environment without significant tidal distortions. Unlike the close binary components of EZ Aquarii, which are tidally locked and rotate synchronously, Struve 2398 A and B rotate independently. Both stars exhibit moderate magnetic activity, with occasional flares and star spots detected in photometric observations. Their rotation periods are estimated at around 30 to 40 days, intermediate between the rapid rotations of young, active red dwarfs and the slow rotations of older, quieter ones. This suggests the system is several billion years old, but still retains enough angular momentum to generate magnetic fields through convective dynamo processes. No planets have been detected around either component of Struve 2398, though the system remains a target for ongoing surveys. Planets could theoretically orbit either star individually, or they could orbit both stars in a circumbinary configuration. However, the relatively wide separation between the stars makes circumbinary planets less likely, as the gravitational influence of both components would create complex orbital dynamics that could destabilize planetary orbits over time. Struve 2398's kinematics have been measured with precision through proper motion and radial velocity studies. The system has a proper motion of about 2.3 arcseconds per year and is moving through space at a velocity of roughly 30 kilometers per second relative to the Sunday. The system is currently moving away from us, gradually increasing its distance over the coming millennia. Spectroscopic analysis reveals that both stars have metallicities, roughly 70% that of the Sun, indicating they formed from gas less enriched by previous stellar generations. This lower metallicity is typical of older stars and consistent with the system's estimated age of 4 to 6 billion years. Despite this age, both stars will continue fusing hydrogen for trillions of years, far outliving more massive stars like the Sunday. Struve 2398 has served as a useful reference for studies of red dwarf binaries and their properties. By observing both components over time, astronomers can measure their orbital motions and use Kepler's laws to determine their masses directly. These measurements provide crucial data for calibrating stellar evolution models, which rely on accurate mass determinations to predict how stars of different masses evolve over time. The system's relative brightness compared to many other red dwarf binaries makes it accessible to smaller telescopes, allowing both professional and amateur astronomers to contribute to its study. Over the decades, hundreds of astrometric measurements have been made, tracing out the star's elliptical orbit and refining estimates of their orbital parameters. Groombridge 34, the double red dwarf. Groombridge 34 is a binary star system located 11.62 light-years from the Sun in the constellation Andromeda. Both components are red dwarfs, designated Groombridge 34A and Groombridge 34B, orbiting each other every 2,600 years. The system was catalogued in the early 19th century by British astronomer Stephen Groombridge as part of his star catalogue, which listed the positions and motions of stars visible from Greenwich Observatory. Groombridge 34A has about 38% of the Sun's mass and a surface temperature around 3,600 Kelvin, making it one of the more massive red dwarfs in the solar neighbourhood. Its luminosity is roughly 1.5% that of the Sun, and it's classified as an M1 5 volts star. Groombridge 34b is smaller and cooler, with about 15% of the Sun's mass, a temperature of approximately 3000 Kelvin, and a luminosity only about 0.2% that of the Sunday. It's classified as an M4V star, placing it among the fainter red dwarfs. The two stars orbit at an average separation of about 147 astronomical units, more than 3 times the distance between the Sun and Pluto. This wide separation means the stars exert minimal gravitational influence on each other, and each can host its own planetary system without significant perturbations from the companion. The orbital period of 2,600 years means the stars move slowly relative to each other, with only a small fraction of their orbit completed since their discovery. Both stars exhibit magnetic activity, though Groombridge 34b is significantly more active. It's classified as a flare star, with frequent eruptions that temporarily increase its brightness. These flares are driven by magnetic reconnection events, similar to those seen on Proxima Centauri and Wolf 359. Groombridge 34a, by contrast, shows only moderate activity, with occasional flares and star spots, but nothing approaching the intensity of its companion. The difference in activity levels between the two stars is likely related to their rotation rates. Faster rotating stars generate stronger magnetic fields and exhibit more frequent flares. Groombridge 34b rotates relatively quickly, with a period estimated at around 10 to 15 days, while Groombridge 34a rotates more slowly, perhaps around 30 to 40 days. These differences illustrate how stellar properties vary, even within binary systems composed of similar stars. No planets have been confirmed around either component, though searches are ongoing. Groombridge 34a, with its relatively high mass and moderate activity, is a favourable target for planet detection. Its larger size makes radial velocity signals easier to detect, and its lower flare rate reduces noise in observational data. Groombridge 34b, with its high activity, presents more challenges, as flares and star spots can mimic or obscure planetary signals. The system's kinematics have been studied extensively. Groombridge 34 has a high proper motion of about 2.9 arcseconds per year, one of the larger proper motions among nearby stars. This motion is caused by its velocity relative to the Sun, estimated at roughly 44 kilometers per second. The system is moving through the Milky Way's disk at an angle, and it's currently approaching the Sunday. In approximately 50,000 years, it will pass within about 9.4 light-years of the solar system before receding again. Spectroscopic studies reveal that both stars have metallicities around 60% with that of the Sun, consistent with ages of several billion years. This lower metallicity suggests the system formed from gas enriched by fewer generations of stars, typical of older stellar populations. Despite their age, both stars will continue shining for trillions of years, remaining on the main sequence long after more massive stars have exhausted their fuel. Epsilon Indi, the K-dwarf with brown dwarf companions. Epsilon Indi is a triple star system located 11.87 light-years from the Sun in the constellation Indus. The primary star, Epsilon Indi A, is a K-type orange dwarf similar to Alpha Centauri b, while the two companions, Epsilon Indi bar and B flat, are brown dwarfs, objects too small to sustain hydrogen fusion but larger than planets. This makes Epsilon Indi one of the nearest systems with confirmed brown dwarf components. Epsilon Indi A has about 77% of the Sun's mass, and a surface temperature around 4,600 Kelvin. It's slightly cooler and less luminous than the Sun, emitting about 22% of the Sun's energy. The star is classified as a K5V dwarf, and is one of the nearest orange dwarfs visible to the naked eye from the southern hemisphere. Despite its proximity and brightness, Epsilon Indi A receives less attention than some other nearby stars, largely because its relatively quiet nature offers fewer dramatic phenomena to study. The star's age is estimated at around 1.3 billion years, making it significantly younger than the Sunday. This youth is reflected in its moderate level of magnetic activity, with occasional flares and star spots detected in photometric observations. However, Epsilon Indi A is far less active than young red dwarfs, as its higher mass and lower rotation rate reduce the efficiency of its magnetic dynamo. In 2003, astronomers using infrared surveys discovered two brown dwarfs orbiting Epsilon Indi A at a distance of about 1,500 astronomical units, roughly 38 times the distance between the Sun and Pluto. These brown dwarfs, designated Epsilon Indi bar and B flat, form a close binary pair, orbiting each other every 15.7 years at a separation of about 2.7 astronomical units. Both are classified as type brown dwarfs, with temperatures around 1,300 to 1,400 Kelvin cooler than L-type brown dwarfs like Lumen 16, but warmer than the coldest Y-type dwarfs like WISE 0855. The masses of Epsilon, Indi bar, and B flat are estimated at 47 and 28 times Jupiter's mass, respectively. Both are below the minimum mass needed to sustain hydrogen fusion, making them true brown dwarfs. At their low temperatures, their atmospheres are dominated by methane and water vapor, similar to the atmospheres of gas giant planets. Spectroscopy has revealed complex chemical processes occurring in their atmospheres, including cloud formation and vertical mixing of gases driven by temperature gradients. The discovery of brown dwarfs around Epsilon Indi A was significant because it demonstrated that such objects can exist in wide orbits around normal stars. Prior to this discovery, most known brown dwarfs were either isolated or members of very close binary systems. Epsilon Indi showed that brown dwarfs can form alongside stars and remain gravitationally bound over billions of years, even at large separations. No planets have been detected around Epsilon Indi A, though searches are ongoing. The star's relative brightness and proximity make it a favourable target for radial velocity and direct imaging surveys. If planets exist, they would likely orbit within a few astronomical units of the star, well inside the orbit of the brown dwarf pair. Epsilon Indi A's kinematics have been measured with high precision. The star has a proper motion of about 4.7 arc-seconds per year and is moving through space at a velocity of roughly 86 kilometers per second relative to the Sunday. The entire system is moving away from us, gradually increasing its distance over the coming millennia. Spectroscopic analysis reveals that Epsilon Indi A has a metallicity slightly lower than the Sun's, about 85% solar abundance. This lower metallicity is consistent with the star's age and suggests it formed from gas that had been somewhat less enriched by previous stellar generations. Despite this, the star's properties closely match those of the Sun in many respects, making it an interesting analogue for studies of solar-type stars. The future of stellar neighbourhood exploration. The study of our nearest stellar neighbours has transformed over the past 2 centuries, evolving from simple distance measurements to detailed characterizations of stellar properties, planetary systems, and brown dwarf companions. Each generation of instruments has revealed new layers of complexity, showing that even the closest stars hold surprises. The dim red dwarfs that dominate our neighbourhood are not the quiet, unchanging objects once imagined, but dynamic, magnetically active systems prone to flares and variability. The brown dwarfs that escape detection for decades blur the boundary between stars and planets, challenging our understanding of how objects form and evolve. And the presence of potentially habitable planets around stars like Proxima Centauri and Ross 128 raises tantalizing questions about whether life exists just beyond our cosmic doorstep. Future missions promise to deepen our knowledge even further. The James Webb Space Telescope, with its powerful infrared capabilities, can study the atmospheres of nearby exoplanets, searching for chemical signatures that might indicate life. Ground-based, extremely large telescopes, now under construction, will directly image planets and brown dwarfs around nearby stars, resolving features on their surfaces and tracking weather patterns in real time. The Nancy Grace Roman Space Telescope will conduct surveys of unprecedented sensitivity, potentially discovering additional ultra-cool dwarfs and rogue planets lurking in the darkness. Advances in propulsion technology may one day allow humanity to visit these neighbouring stars. Concepts like laser-driven light sails, nuclear pulse propulsion, and fusion drives remain theoretical but are grounded in known physics. A spacecraft travelling at 10 to 20% of the speed of light could reach Alpha Centauri within a few decades, returning data and images of alien worlds that currently exist only in our imaginations. Such missions would represent the first steps toward becoming an interstellar civilization, expanding our presence beyond the solar system and into the broader galaxy. The nearest stars are not distant, unreachable objects, but neighbours in a vast cosmic community. They shape the structure of the local interstellar medium, influence the trajectories of comets and asteroids in the Oort cloud, and provide benchmarks for understanding stellar physics across the universe. By studying them in detail, astronomers calibrate the tools and theories needed to explore the Milky Way and beyond, building a foundation of knowledge that stretches from our solar system to the most distant galaxies. Each of these stars tells a story of formation, evolution, and eventual death. Some, like Sirius A and Procyon A, are racing toward their final transformation into white dwarfs, burning through their fuel in mere hundreds of millions of years. Others, like Proxima Centauri and Ross 128, have barely begun their lives and will continue shining for trillions of years, outlasting every massive star in the galaxy. Brown dwarfs like Lumen 16 and Y0855 represent failed attempts at stardom, objects that never quite made it but remain fascinating in their own right. Together, they form a diverse stellar ecosystem, a sample of the galaxy's population concentrated within a tiny bubble of space surrounding our Sunday. The exploration of our stellar neighbourhood continues, driven by curiosity, advancing technology, and the timeless human desire to understand our place in the universe. With each new discovery, the cosmos reveals itself to be more complex, more dynamic, and more wondrous than we imagined. The stars that surround us are not mere points of light, but worlds unto themselves, each with its own history, its own characteristics, and perhaps even its own planets hosting life. In studying them, we study ourselves, learning how stars and planets form, how life arises, and how the universe evolves over the vast stretches of cosmic time. The journey to the nearest stars has only just begun. Designated Struve 2398A and Struve 2398b, orbiting each other every 295 years. Struve 2398 A is slightly more massive, with about 29% of the Sun's mass and a surface temperature around 3,500 Kelvin. Struve 2398 B is somewhat smaller, containing about 26% of the Sun's mass with a similar temperature. Both stars are classified as M3V dwarfs, placing them in the mid-range of red dwarf properties, cooler and less massive than stars like Ross 128, but warmer and more luminous than ultra-cool dwarfs like Proxima Centauri. The two stars orbit at an average separation of about 55 astronomical units, roughly the distance between the Sun and the outer edge of the Kuiper belt. This relatively wide separation means gravitational interactions between the stars are weak, and each maintains its own environment without significant tidal distortions. Unlike the close binary components of easy Aquarii, which are tidally locked and rotate synchronously, Struve 2398a and b rotate independently. Both stars exhibit moderate magnetic activity, with occasional flares and star spots detected in photometric observations. Their rotation periods are estimated at around 30 to 40 days, intermediate between the rapid rotations of young, active red dwarfs and the slow rotations of older, quieter ones. This suggests the system is several billion years old, but still retains enough angular momentum to generate magnetic fields through convective dynamo processes. No planets have been detected around either component of Struve 2398, though the system remains a target for ongoing surveys. Planets could theoretically orbit either star individually, or they could orbit both stars in a circumbinary configuration. However, the relatively wide separation between the stars makes circumbinary planets less likely, as the gravitational influence of both components would create complex orbital dynamics that could destabilize planetary orbits over time. Struve 2398's kinematics have been measured with precision through proper motion and radial velocity studies. The system has a proper motion of about 2.3 arcseconds per year and is moving through space at a velocity of roughly 30 kilometers per second relative to the Sunday. The system is currently moving away from us, gradually increasing its distance over the coming millennia. Spectroscopic analysis reveals that both stars have metallicities, roughly 70% that of the Sun, indicating they formed from gas less enriched by previous stellar generations. This lower metallicity is typical of older stars and consistent with the system's estimated age of 4 to 6 billion years. Despite this age, both stars will continue fusing hydrogen for trillions of years, far outliving more massive stars like the Sunday. Struve 2398 has served as a useful reference for studies of red dwarf binaries and their properties. By observing both components over time, astronomers can measure their orbital motions and use Kepler's laws to determine their masses directly. These measurements provide crucial data for calibrating stellar evolution models, which rely on accurate mass determinations to predict how stars of different masses evolve over time. The system's relative brightness, compared to many other red dwarf binaries, makes it accessible to smaller telescopes, allowing both professional and amateur astronomers to contribute to its study. Over the decades, hundreds of astrometric measurements have been made, tracing out the star's elliptical orbit and refining estimates of their orbital parameters. Groombridge 34, the double red dwarf. Groombridge 34 is a binary star system located 11.62 light-years from the Sun in the constellation Andromeda. Both components are red dwarfs, designated Groombridge 34a and Groombridge 34b, orbiting each other every 2,600 years. The system was catalogued in the early 19th century by British astronomer Stephen Groombridge as part of his star catalogue, which listed the positions and motions of stars visible from Greenwich Observatory. Groombridge 34a has about 38% of the Sun's mass and a surface temperature around 3,600 Kelvin, making it one of the more massive red dwarfs in the solar neighborhood. Its luminosity is roughly 1.5% that of the Sun, and it's classified as an M15 volt star. Groombridge 34b is smaller and cooler, with about 15% of the Sun's mass, a temperature of approximately 3,000 Kelvin, and a luminosity only about 0.2% that of the Sunday. It's classified as an M4V star, placing it among the fainter red dwarfs. The two stars orbit at an average separation of about 147 astronomical units, more than 3 times the distance between the Sun and Pluto. This wide separation means the stars exert minimal gravitational influence on each other, and each can host its own planetary system without significant perturbations from the companion. The orbital period of 2,600 years means the stars move slowly relative to each other, with only a small fraction of their orbit completed since their discovery. Both stars exhibit magnetic activity, though Groombridge 34b is significantly more active. It's classified as a flare star with frequent eruptions that temporarily increase its brightness. These flares are driven by magnetic reconnection events similar to those seen on Proxima Centauri and Wolf 359. Groombridge 34a, by contrast, shows only moderate activity, with occasional flares and star spots, but nothing approaching the intensity of its companion. The difference in activity levels between the two stars is likely related to their rotation rates. Faster rotating stars generate stronger magnetic fields and exhibit more frequent flares. Groombridge 34b rotates relatively quickly, with a period estimated at around 10 to 15 days, while Groombridge 34a rotates more slowly, perhaps around 30 to 40 days. These differences illustrate how stellar properties vary even within binary systems composed of similar stars. No planets have been confirmed around either component, though searches are ongoing. Groombridge 34a, with its relatively high mass and moderate activity, is a favourable target for planet detection. Its larger size makes radial velocity signals easier to detect, and its lower flare rate reduces noise in observational data. Groombridge 34b, with its high activity, presents more challenges, as flares and star spots can mimic or obscure planetary signals. The system's kinematics have been studied extensively. Groombridge 34 has a high proper motion of about 2.9 arcseconds per year, one of the larger proper motions among nearby stars. This motion is caused by its velocity relative to the Sun, estimated at roughly 44 kilometers per second. The system is moving through the Milky Way's disk at an angle, and it's currently approaching the Sunday. In approximately 50,000 years, it will pass within about 9.4 light-years of the solar system before receding again. Spectroscopic studies reveal that both stars have metallicities around 60% that of the Sun, consistent with ages of several billion years. This lower metallicity suggests the system formed from gas enriched by fewer generations of stars, typical of older stellar populations. Despite their age, both stars will continue shining for trillions of years, remaining on the main sequence long after more massive stars have exhausted their fuel. Epsilon Indi, the K-dwarf with brown dwarf companions. Epsilon Indi is a triple star system located 87 light-years from the Sun in the constellation Indus. The primary star, Epsilon Indi A, is a K-type orange dwarf similar to Alpha Centauri b, while the two companions, Epsilon Indi Bar and B Pli, are brown dwarfs objects, too small to sustain hydrogen fusion, but larger than planets. This makes Epsilon Indi one of the nearest systems with confirmed brown dwarf components. Epsilon Indi A has about 77% of the Sun's mass and a surface temperature around 4,600 Kelvin. It's slightly cooler and less luminous than the Sun, emitting about 22% of the Sun's energy. The star is classified as a K5b dwarf and is one of the nearest orange dwarfs visible to the naked eye from the southern hemisphere. Despite its proximity and brightness, Epsilon Indi A receives less attention than some other nearby stars, largely because its relatively quiet nature offers fewer dramatic phenomena to study. The star's age is estimated at around 1.3 billion years, making it significantly younger than the Sunday. This youth is reflected in its moderate level of magnetic activity, with occasional flares and star spots detected in photometric observations. However, Epsilon Indi A is far less active than young red dwarfs, as its higher mass and lower rotation rate reduce the efficiency of its magnetic dynamo. In 2003, astronomers using infrared surveys discovered two brown dwarfs orbiting Epsilon Indi A at a distance of about 1,500 astronomical units, roughly 38 times the distance between the Sun and Pluto. These brown dwarfs, designated Epsilon Indi bar and B flat, form a close binary pair, orbiting each other every 7 years at a separation of about 2.7 astronomical units. Both are classified as type brown dwarfs, with temperatures around 1,300 to 1,400 Kelvin cooler than L-type brown dwarfs like Lumen 16, but warmer than the coldest Y-type dwarfs like WISE 0855. The masses of Epsilon, Indi bar and Biflat are estimated at 47 and 28 times Jupiter's mass, respectively. Both are below the minimum mass needed to sustain hydrogen fusion, making them true brown dwarfs. At their low temperatures, their atmospheres are dominated by methane and water vapor, similar to the atmospheres of gas giant planets. Spectroscopy has revealed complex chemical processes occurring in their atmospheres, including cloud formation and vertical mixing of gases driven by temperature gradients. The discovery of brown dwarfs around Epsilon Indi A was significant because it demonstrated that such objects can exist in wide orbits around normal stars. Prior to this discovery, most known brown dwarfs were either isolated or members of very close binary systems. Epsilon Indi showed that brown dwarfs can form alongside stars and remain gravitationally bound over billions of years, even at large separations. No planets have been detected around Epsilon Indi A. Though searches are ongoing, the star's relative brightness and proximity make it a favourable target for radial velocity and direct imaging surveys. If planets exist, they would likely orbit within a few astronomical units of the star, well inside the orbit of the brown dwarf pair. Epsilon Indi A's kinematics have been measured with high precision. The star has a proper motion of about 4.7 arc-seconds per year and is moving through space at a velocity of roughly 86 kilometers per second relative to the Sunday. The entire system is moving away from us, gradually increasing its distance over the coming millennia. Spectroscopic analysis reveals that Epsilon Indi A has a metallicity slightly lower than the Sun's, about 85% solar abundance. This lower metallicity is consistent with the star's age and suggests it formed from gas that had been somewhat less enriched by previous stellar generations. Despite this, the star's properties closely match those of the Sun in many respects, making it an interesting analogue for studies of solar-type stars. Tau Ceti, the Sun's near twin with a crowded debris system. At a distance of 11.91 light-years, Tau Ceti stands as one of the most scrutinized stars in our stellar neighborhood. Located in the constellation Cetus, the Whale, it ranks among the closest single stars similar to our Sun, a rarity in a neighbourhood dominated by dim red dwarfs and binary systems. With about 78% of the Sun's mass and a surface temperature of approximately 5,300 Kelvin, Tau Ceti belongs to the spectral class G8V, making it slightly cooler and less luminous than our home star, but remarkably similar in fundamental properties. This resemblance has made it a perennial favourite in both scientific research and popular culture, appearing in countless science fiction stories as a plausible home for alien civilizations. What distinguishes Tau Ceti from the Sun, however, is not its similarities, but its dramatic differences. The star is surrounded by one of the most massive debris disks ever detected. Around a Sun-like star, a vast ring of dust and rocky material that dwarfs anything remaining in our own solar system. This disk extends from about 55 to 200 astronomical units, far beyond the orbit of Neptune, and contains at least 10 times more material than the Sun's asteroid belt and Kuiper belt combined. The sheer density of this debris suggests a chaotic environment where collisions between asteroids and comets occur far more frequently than in our solar system, producing a constant rain of dust and fragments. The discovery of Tau Ceti's debris disk came from infrared observations by space telescopes like Spitzer and Herschel, which detected the thermal glow of dust particles warmed by starlight. The disk's structure reveals asymmetries and clumps that hint at gravitational perturbations from unseen planets, similar to how Neptune shapes the Kuiper belt in our solar system. These features suggest that Tau Ceti likely hosts a planetary system, though the planets themselves have proven maddeningly difficult to confirm. Starting in 2012, astronomers began reporting possible detections of multiple planets around Tau Ceti using the radial velocity method. Initial claims suggested as many as 5 planets, with masses ranging from 2 to 6 times Earth's mass, orbiting at distances between 0.1 and 1.4 astronomical units. 2 of these candidates, designated Tau Ceti A and Tau Ceti F, appeared to orbit within or near the star's habitable zone, the region where temperatures might permit liquid water on a planetary surface. The prospect of potentially habitable worlds around such a nearby, Sun-like star generated tremendous excitement. However, subsequent observations have cast doubt on these claims. The signals attributed to planets are extremely weak. Tau Ceti's radial velocity changes by only about 1 meter per second due to the gravitational influence of these potential worlds, roughly the speed of a person walking slowly. At such low amplitudes, stellar activity becomes a critical concern. Stars like Tau Ceti exhibit magnetic cycles, star spots, and other forms of variability that can produce radial velocity signals mimicking those of planets. Distinguishing genuine planetary signatures from stellar noise requires years of high-precision measurements and sophisticated statistical analysis. Recent studies have suggested that some or all of the reported planets may be artifacts of stellar activity rather than real worlds. The debate remains unresolved, illustrating the profound challenges of detecting small, rocky planets around stars with even moderate levels of magnetic activity. Unlike the quiet red dwarf Ross 128, which makes planet detection relatively straightforward, Tau Ceti's sun-like nature brings with it the complications of stellar variability that plague radial velocity searches. If planets do exist around Tau Ceti, they face a harsh environment. The massive debris disk implies that the inner system is subject to frequent asteroid and comet impacts, far more so than Earth experienced even during the late heavy bombardment 4 billion years ago. Any planet orbiting Tau Ceti would be bombarded by impactors at rates potentially hundreds of times higher than in our solar system. Such intense cratering could sterilize planetary surfaces repeatedly, making the emergence and persistence of life extraordinarily difficult unless planets possess thick atmospheres or strong magnetic fields to deflect some of the incoming debris. This collision-rich environment raises fundamental questions about planetary habitability. While asteroid impacts delivered water and organic molecules to early Earth, contributing to the conditions that allowed life to arise, excessive bombardment can have the opposite effect. Impacts energetic enough to vaporize oceans or strip away atmospheres would reset the clock on biological evolution, preventing complex life from gaining a foothold. Tau Ceti's planets, if they exist, may represent worlds in a perpetual state of trauma, constantly recovering from catastrophic impacts. Tau Ceti's age, estimated at around 5.8 billion years, means it's significantly older than the Sunday. Despite this age, the debris disk remains remarkably dense, suggesting ongoing replenishment from a large reservoir of comets and asteroids. In our solar system, the Kuiper belt has been gradually depleted over billions of years through collisions and gravitational ejections. Tau Ceti's disk, by contrast, appears to retain a much larger population of objects, possibly because its planets, if they exist, are too small or too few to efficiently clear the debris. Spectroscopic analysis reveals that Tau Ceti has a metallicity only about 28% that of the Sun, making it metal poor compared to most nearby solar-type stars. This low metallicity is puzzling given the star's youth. Metal-poor stars typically belong to older stellar populations that formed when the galaxy contained fewer heavy elements. Tau Ceti's composition suggests it may have formed from gas less enriched by previous supernovae, or that some dynamical process depleted its metal content. This lower metallicity has implications for planet formation, as heavy elements provide the raw material for building rocky planets. The reduced abundance of metals may explain why Tau Ceti's planets, if confirmed, appear to be relatively small. The star's proper motion of about 1.9 arc-seconds per year indicates it's moving through space at approximately 37 kilometers per second relative to the Sunday. Tau Ceti is currently approaching our solar system, though slowly. In roughly 43,000 years, it will reach its closest approach at about 10.6 light-years before receding again. This gradual approach makes it an increasingly favourable target for future observations and potential interstellar missions. Tau Ceti's proximity, stability, and similarity to the Sun have made it a target for searches for extraterrestrial intelligence. Radio telescopes have monitored the star multiple times over the decades, listening for artificial signals that might indicate an advanced civilization. Despite these efforts, no confirmed detections have been made. The star's dense debris environment and uncertain planetary system leave open the question of whether technological life could arise and survive in such a hazardous setting. The future of stellar neighbourhood exploration. The study of our nearest stellar neighbours has transformed over the past 2 centuries, evolving from simple distance measurements to detailed characterizations of stellar properties, planetary systems, and brown dwarf companions. Each generation of instruments has revealed new layers of complexity, showing that even the closest stars hold surprises. The dim red dwarfs that dominate our neighbourhood are not the quiet, unchanging objects once imagined, but dynamic, magnetically active systems prone to flares and variability. The brown dwarfs that escape detection for decades blur the boundary between stars and planets, challenging our understanding of how objects form and evolve. And the presence of potentially habitable planets around stars like Proxima Centauri and Ross 128 raises tantalizing questions about whether life exists just beyond our cosmic doorstep. Future missions promise to deepen our knowledge even further. The James Webb Space Telescope, with its powerful infrared capabilities, can study the atmospheres of nearby exoplanets, searching for chemical signatures that might indicate life. Ground-based, extremely large telescopes, now under construction, will directly image planets and brown dwarfs around nearby stars, resolving features on their surfaces and tracking weather patterns in real time. The Nancy Grace Roman Space Telescope will conduct surveys of unprecedented sensitivity, potentially discovering additional ultra-cool dwarfs and rogue planets lurking in the darkness. Advances in propulsion technology may one day allow humanity to visit these neighboring stars. Concepts like laser-driven light sails, nuclear pulse propulsion, and fusion drives remain theoretical but are grounded in known physics. A spacecraft travelling at 10 to 20% of the speed of light could reach Alpha Centauri within a few decades, returning data and images of alien worlds that currently exist only in our imaginations. Such missions would represent the first steps toward becoming an interstellar civilization, expanding our presence beyond the solar system and into the broader galaxy. The nearest stars are not distant, unreachable objects, but neighbours in a vast cosmic community. They shape the structure of the local interstellar medium, influence the trajectories of comets and asteroids in the Oort cloud, and provide benchmarks for understanding stellar physics across the universe. By studying them in detail, astronomers calibrate the tools and theories needed to explore the Milky Way and beyond, building a foundation of knowledge that stretches from our solar system to the most distant galaxies. Each of these stars tells a story of formation, evolution, and eventual death. Some, like Sirius A and Procyon A, are racing toward their final transformation into white dwarfs, burning through their fuel in mere hundreds of millions of years. Others, like Proxima Centauri and Ross 128, have barely begun their lives and will continue shining for trillions of years, outlasting every massive star in the galaxy. Brown dwarfs like Lumen 16 and Y0855 represent failed attempts at stardom, objects that never quite made it but remain fascinating in their own right. Together, they form a diverse stellar ecosystem, a sample of the galaxy's population concentrated within a tiny bubble of space surrounding our Sunday. The exploration of our stellar neighbourhood continues, driven by curiosity, advancing technology, and the timeless human desire to understand our place in the universe. With each new discovery, the cosmos reveals itself to be more complex, more dynamic, and more wondrous than we imagined. The stars that surround us are not mere points of light, but worlds unto themselves, each with its own history, its own characteristics, and perhaps even its own planets hosting life. In studying them, we study ourselves, learning how stars and planets form, how life arises, and how the universe evolves over the vast stretches of cosmic time. The journey to the nearest stars has only just begun.